Hi everyone, welcome to the PCD of Codechef Starters 169. I am Pradyumn Kejriwal and this is TLE Eliminators, and let's get started. So today we'll discuss the first three problems, that is A, B, and C. Um, Personally, the contest felt somewhat unbalanced. Like the problems A, B, and C were quite easy or easy to medium level, but this D and D onwards had like only two solves. So it was quite unbalanced, the contest. So even I couldn't solve D. So today we'll discuss the first three of them. Okay. All right. So the first problem is this. Uh, yeah, okay, yeah. So this is the first problem. That is, you are given a permutation P of length n. You are allowed to perform the following operation any number of times. Choose two numbers, Pi and Pj, such that the number of set bits is in both of them is same, and then swap them. Determine if it is possible to sort the permutation in ascending order using this operation. If possible, print yes, otherwise print no. Okay, so the problem says that there is a permutation. What is a permutation? Permutation means that any ordering of numbers from 1 to n. Like for example, if n is 3, then let's say we have 3, 1, 2. So this is a permutation. 2, 3, 1. This is also a permutation. And we have been told that we have to sort the permutation. And to do that, we can use only one operation, which is that we can select I and j and we can swap pi and pj. But we can do this only if the number of bits in pi, number of set bits, like that is the number of bits that are 1 in pi, should be equal to the number of set bits in pj. Okay. So this is the operation that we can do. We can do this operation if and only if the bits of pi is equal to bits of pj. All right. Okay, so we want to figure out that whether we can sort the permutation or not. All right. Okay, so let's see. So let's do the samples. Okay, the samples. This one is pretty useless. This one is okay. We can look. Let's look at this one. 4132. Okay. So the permutation is 4132, right? Now, basically, what we want to do, we want to have one here, right? We want to sort the permutation, which means that the permutation should become like 1, 2, 3, 4, right? So basically we want that one should be here, right? So let's just swap 4 and 1, and we can do that because 4 in base 10, like the binary of 4 is just 100, right? And binary of 1, that is just 1, right? So both of these have the same number of set bits, that is only one set bit. So we can swap 4 and 1. So let's just do that. 1, 4, 3, 2. Now let's say we want 2 here, right? So if we can swap 4 and 2, then that would be great. So we can actually, because 4 is 100 and 2 is 10. So we can swap 4 and 2 because both of them have only one bit, one set bit in their arrangement, in their representation. So it will become 1, 2, 3, and 4. And so this has become sorted array, right? So yes, as someone said in the chat, how they solved it, that is actually correct. So I'll just explain it. So first of all, you can only swap those indices which have the same number of set bits, right? So let's say let's say suppose n is equal to 7. I'll make a test case. Okay. First of all, I'll write all the representations of numbers up to 7. Okay. So one is just 1, 2 is 10, 3 is 1, and so on. I'll write till 7. Okay. Just to explain, 100, 101, 6 is 110, and 7 is 111. So let's say n is 7. So basically, 6, like 6 has 2. So I'll write the number of set bits in these: 2, 2, 1, 2, 1, 1, and 3. All right. So let's take a permutation. Okay. I'll just make a sample test case. Right. So what should I make? Let's see. Let's say we have 2, 1, 3, 7, 4, 6, 5. So this is the permutation, right? Now let's just write their number of set bits between them. Okay. So 2 has 1, 1 has 1, 3 has 2, 7 has 3, 4 has 1, 6 has 2, and 5 has 2. So basically, actually, if you look carefully, the operation says that we can only swap I and j if the number of set bits in pi and pj is same. So basically, this 3, 6, and let's say we have this 3, 6, and 5. Both of them have 2, right? In the number of set bits. So we can only shuffle these numbers in only these positions. We cannot bring them to other positions where the like 3 or 1 is there. We cannot bring them. We cannot bring them there. That is the observation here. Like we can make any permutation of 3, 6, and 5, but they can only belong to these three indices. Like we can do something like 6 comes here, 5 comes here, 3 comes here. Like this is possible to do, but it is not possible that 6 comes here, because we can never move something which has 3 bits out of here. Like definitely something else which comes to this position will have 3 bits. So we can always say that it is only possible to shuffle these numbers only in these three indices, right? So therefore we just need to check that the permutation that we want to make, like what is that? We want to make one, like the sort permutation, right? 1 to n, 1, 2, 3, 4, 5, 6, and 7. So we can only do this if at all the indices the number of set bits of the number that we want is equal to the number of set bits of the actual number. Like here 1 and 2 both have 1 bit, so definitely we can bring 1 here somehow. Then again 1 and 2 both have same bit, 3 and 3 are the same. Then 4 and 7. Okay, here comes the uh, problem, right? Because 4 has 2 bits, sorry, 4 has 1 set bit, and 7 has 3 set bits. So we can never move 4 to this index, because we would have to swap 7 with something else, or basically whatever we swap 7 with, it will always have 3 bits set. So we can never swap 7 with 4, or whatever it is here, like whatever number is here, we cannot swap it with 4, because 4 doesn't have 3 set bits. So that's what we have to do. We just have to check that for every index it should have the correct number of set bits. Like basically for index I, like if I am talking in one indexing, then the number of bits set in p of I, like this is p of I, right? This is p, and this is just identity permutation. This is, let's say this is I. So number of set bits in p of I should be equal to I for all the indexes. Like the number of set bits in p of I should be equal to number of set bits in I, like if I'm talking in one indexing. If in zero indexed, then just for all I from 0 to n minus 1, number of set bits in p of I should be equal to bits of I plus 1. Like this is for zero indexing. So that's the case. And actually, yeah, so bits pi should be equal to bits of I plus 1. And basically there's a function in C++ which can give you the number of bits in a number. So that is called underscore underscore built-in pop count. builtin underscore pop count. So using this function, you can calculate the bits. So for each index I, you traverse through the array and check that this holds true or not. So if at any point this doesn't hold true, then you can just print no. And otherwise, if it holds true for all the indices, then you print yes. I hope you understand. So do any of you have a doubt in this approach? Okay, show us the code. Yes, I will do that. Um, okay, let's show the code first, then I'll address the other doubts. Uh, okay. So this is very simple. So LLN, take the input. I take the input of the array, and I loop through the array. Like for I is equal to 0, I less than n, I less than n, I plus plus. This is the macro. So if built-in pop count of AI is not equal to built-in pop count of I plus 1, like this is what I told you. If it is not equal, then you can just print no and return. And if you don't return from this, that means all of them are true. They are all equal. So you print yes. Okay. So this is the code. Any doubts in the code? All right. So someone is asking me, can't we apply merge sort here and just change the condition? Merge sort, like I don't quite understand how you apply merge sort. Can you elaborate a bit? That how are you applying merge sort here? Someone said didn't know about built-in pop count. Okay, yeah, this is a very useful function. And actually, there are two more functions which are there. Like the first function is built-in pop count, and the other one I'll just write it here. It is called built-in CLZ. So that just counts the leading zeros. What is leading zero? Like for example, if for an integer, int has 32 bits, right? Int has 32 bits. So if let's say you calculate built-in CLZ of 4. So what is 4 in binary? It is 100. So basically there are 100 and there are some leading zeros also, right? So there are 29 zeros here because these 3 bits are here and rest 29, they are zeros. So built-in CLZ of 4 will return 29. And also there is something called built-in CTZ. Built-in CTZ of n, that just counts the number of trailing zeros. So for 4 it will return 2 zeros. And just make sure that n is greater than 0. These functions don't work for n equal to 0. Someone is asking me to explain the condition. Okay, I'll explain. So basically, do you get till here? Like this, I explained that we the currently our permutation is something, the input, right? And we want to make it from 1 to n. We want to sort it. So we want to make it like this. So at each step, the thing that we want to make should have same number of bits as the thing that we currently have. Like 2 and 1 should have equal number of set bits, 1 and 2 should have equal number of set bits, 3 and 3 equal, 7 and 4 equal number of set bits, like they should have. In that case only we can sort the permutation. So do you get this part, or do you want me to explain this part only? This part is clear. Okay, so to check this, you can just like, so we want to iterate over, basically what we want to make. We want to make this 1, 2, 3, 4, 5, 6, and 7. So what I am doing is I am iterating over the permutation. Okay. So let's say this is P of 0, right? P of 0 is 2. I'll just write the index here. 0, 1, 2, 3, 4, 5, 6. So P of 0 is 2. So I'll just check that is 2 equal to 1. And why 1? Like basically whatever we want to make. So at index I, as you can see, we want to make I plus 1. Like at 0 we want to make 1. At 1 we want to make 2. At 2 we want to make 3, and so on. So that's why I am comparing P of I to I plus 1. Okay, cool. Okay, someone told me the logic of merge sort. So basically, as we do in merge sort, we break down the array, and if the condition satisfies, then we swap. In merge sort, we don't do swaps, right? We merge two sub arrays or two smaller arrays to make a bigger one. Actually, I don't really understand what you are asking. So could you just ask that in the doubt section of TLE? Someone will help you out there. Okay. So let's move on to the next problem. Actually, I think this was problem 2, right? It has more solves somehow. Anyways, so I discussed this one first. Now let's discuss problem A. So the problem A goes like, you are given an array A of n integers. You can perform the following operation any number of times. Select and remove any prefix or suffix of the array A, but not the entire array. Your goal is to determine the minimum number of operations required to make k the most frequent element in the array A. It is guaranteed that k is initially present in the array. Okay, so this problem says that we have an array. Let's take the samples. Let's take one sample of this one, 1, 1, 3, 2, 2. This array is given and k is given to be 3, right? So basically the problem is asking that in one operation, either we can delete a prefix of the array of any length, whatever length we want, we can delete that prefix, or in one operation we can delete a suffix of the array of any length, but not the entire array. That is the condition. Like in one operation, we can either delete a prefix or we can delete a suffix, right? And we have to make sure that this k, like k is given to be 3, so we have to make sure that 3 is the most frequent element, or rather 3 is one of the most frequent elements, like because there can be multiple elements which have the highest frequency, right? So we have to make 3 one of the most frequent elements. Okay, so in this case what we can do, let's say we delete this prefix of 1, so this gets deleted, and we delete this suffix of 2, so this 2 gets deleted. So the array that we are left with, that is 1, 3, and 2. So in this array, the frequency of 1, the frequency of 3, and frequency of 2, all of those 3 are 1. The frequency is equal to 1. So therefore 3, that is k, is one of the most frequent elements. Like the most frequent elements have frequency 1, and 3 also has frequency 1. So it is the most frequent element in the array. And or also we could have, what we could have done is, we could have deleted this whole prefix. Wait a minute. We could delete this whole prefix. Okay, and we could delete this whole suffix. So in this case, what we would be left with would be just 3. So definitely 3 is the most frequently occurring element. in this array because it is the only element. Like the frequency of 3 is 1 and other ones is 0. So therefore 3 is the most frequently occurring. Okay. Just a minute. All right. So basically, in one operation, we can, yes, we can either delete prefix or suffix. We can't delete both at the same time. I mean, in one operation, you can delete either prefix or suffix. That is the point. So basically, I am taking two operations here. My point is that if I do this and then do this, so we are taking two operations there. So two is the answer actually, because we can't do it in one operation. Okay. So this is actually similar problem to, actually, never mind. I'll just explain the intuition here. Okay. So basically, the prefix and suffix thing is very trivial actually. Like, let's say you have an array. Suppose first you delete this prefix, then you delete this suffix, then you delete this prefix, then this prefix. So actually, these three prefixes operations we can actually merge into one, right? Like instead of doing this prefix three times, we can take this entire prefix in just one operation. So definitely, it is not optimal to apply more than one prefix and more than one suffix. Like if we are doing that, we can just do it in one operation instead. So definitely, we can select a subarray. Like we can select any subarray using just two operations, one prefix operation and one suffix operation, right? So actually, so we can actually do it in two operations only, like always. Like basically, we have some number k, right? So and it is guaranteed that it occurs in the array. It is guaranteed that k is initially present in the array. So we can just delete all the elements before it. Like let's say k is somewhere here. Let's say k is here. Then we can just remove this subarray. I mean this prefix and this suffix, and we would be left with this k. And therefore, definitely k would be the highest frequent, like the most frequently occurring element here, right? So definitely we can always do it in two operations. So we want to find the minimum operations, right? So we found a way to always do it in two operations. Now we just have to figure out that whether there exists a sequence of one or zero operations or not, right? So either one operation or zero operation, is it possible? So we can just check that. So if zero operations, that means that initially, like zero operation means that we aren't deleting anything. So that means that in the initial array, k was the most frequent. Like in the original array only, k was the most frequent. Like let's say there was some k, let's say k is equal to 1. Okay. So there is some 1 here, 1 here, 1 here, 2 here, 2 here, and 3 here. So initially 1 is the most frequent in this array. So we don't need to delete anything. So we don't need to make any operation. So here the answer is 0. Okay. So we'll just check that. And if 0 is not possible, 0 not possible means that initially k is not the most frequent. So to check, so basically you have to check that is the answer 1 or not. Because we can always do it in two operations. We can check that is the answer 1. So how to do that? Basically one operation, what does that mean? That means that either we are deleting an entire prefix or we are deleting an entire suffix. Okay. So we can just check all the prefixes and all suffixes. That will take O of n time. Like how do we do that? I'll just explain how to do that. Okay. So actually we can do that using a frequency array. So wait, so basically I'll summarize what I said. I said that we need to check. So first of all, we checked if zero operations is correct. So if it is not, then we need to check that if is one operation is correct. When would be one operation correct? That would be when we are deleting a prefix and a suffix. Like for example, 2 1 1 3 1 2. So one would be correct when either we are deleting an entire prefix or an entire suffix, right? So we can just check that does, like, can a case like that happen. So how do we do that? So basically what we can do is we can make a frequency array. Okay, so frequency array will look like, initially frequency of 1 will be 3, frequency of 2 will be 2, and frequency of 3 will be equal to 1. So now we can actually iterate. Like, first of all, we can try deleting this prefix. So what would that have, what will that do? That will make the frequency of this to be 1. So now we check, is 1 the most frequent? Actually, sorry, initial, in this case initial array is correct only. So let's just do this. Okay, so initially fr of 1 is 1, fr of 2 is 3. Okay, so yeah, we first delete this element. So the frequency of 2 decreases to 2 because this is deleted, right? Then we check that did 1 become the first, like k is equal to 1. Okay, so we check that did 1 become the maximum. So no, it is not the maximum because 2 is the maximum. 2 is the most frequent, right? So now we delete this 2 also. We try to check that is 1 still the maximum. So basically, and yes, 1 becomes the maximum because the maximum value is maximum frequency. Okay, I messed up. Initially it should have been, okay, just ignore this part. Now I am correct. Initially it was 3, then it became 2, then now it became 1. So now the maximum frequency is 1 and 1 has maximum frequency. So it is correct. So basically what we found out is that this prefix has the maximum, like this prefix, if we delete this prefix, then we'll be left with an array which will have the most frequency of k, like fr of k will be maximum. So therefore in that case 1 would be the answer. So that's how we check for prefixes. And how do we check for suffixes? In the same way, we just iterate in the reverse order. Like for example, if we have this and this, we have 2 1 2 3 2. So first of all, we make a frequency array. Frequency array, what will it look like? It will look something like 1 will have frequency 1, 2 will have frequency of 3, and 3 has frequency of 1, right? Now we iterate from the back. Like, we first of all try deleting this subarray, this suffix. So 2 will have frequency of 2. So we don't, like, it is not the maximum. 1 is not the maximum, 2 is the maximum, right? Now we try to delete this 3. So it will become 0, but still 1 is not the maximum. Now we delete this 2. So now 2 becomes 1. So therefore 1 becomes the maximum. So in this case, the suffix has an answer. Like, if we delete this suffix, then it will make 1 the maximum element. So therefore we have an answer of 1. So we just need to check that does deleting a suffix, can we do that and get the maximum frequency? And if we cannot, like if we cannot delete either a prefix or a suffix, then definitely we can do it in 2 operations. That method I just discussed, that let's say there is some k here, then we'll just delete this prefix and this suffix. So we'll just be left with the element k in the array, and therefore it would be the most frequent element. So this is the conclusion, that basically we check for 0 first, then we check for 1 first, and if both of these are false, then 2 is the answer, because we can always do it in 2 operations, right? So I'll just show you the code first, and then we can check the doubts if someone has any doubts. Okay. And yeah, in this case, actually, checking the maximum frequency, that will take O of AI time. Like, let's say you have the frequency table, right? You have the frequency array. So when you are checking for every prefix, for example, you are updating this frequency array every time. So let's say you delete this element. So you decrease the frequency of this element by 1. Then you have to check in the entire frequency array what is the maximum element. So if this frequency array is of size s, then it will take O of s time, and you are doing this in each iteration, right? So it will be O of n into s to check for prefix, and same for suffix. So AI, yes, AI can be max 20. That's why the constraints are given like that. That the AI range is 1 to 20. So we don't need to make a frequency array very large. We can just make it of size 21 so that we can accommodate all the numbers. So the solution has an O of n into s time complexity, right? Actually, we can do better. We can do it in O of n log s also. Like we can just maintain a set, or a multi-set rather. We can maintain a multi-set which will contain all of the elements of this frequency array. And let's say we want to delete, like, or we want to decrease some element of this frequency array by 1. Then we can just, let's say we want to initially frequency array look like something like 1 2 3. 1 2 3 has frequency 5 4 and 12. Now let's say we want to remove the 2 element, so we want to change this 4 to a 3, right? So actually um we could have had a set which has 5 4 and 12. This is a set s that we had made. And basically when you want to like decrease an element, so you want to make this 4 as 3. So in this set also we'll remove this 4 and insert a 3. That can be done in O of log s, log of s, I mean the size of s, which is s, right? So that's why in every iteration you can check that in what is the minimum element in O of log s, right? So that's how you can do it in, like, even if this constraint wasn't there, you can easily do it, right? You can just create a map of frequency and a set of those elements, right? So let's just, I didn't do it because the constraints were low. So I'll show you the code. Okay. Sorry. Anyways, so this is the thing. I took n and k as an input, then I took the array, and this is the frequency array of 21. And for each element in AI, like in A, I increased its frequency, fr of AI plus plus. So now this is check for 0. Like if already the star max element, like this max element function returns the iterator to the maximum element. And so I dereference the iterator. And if that is equal to frequency of k, then C out 0. Okay, someone is asking in O of 1 space, we can do this, right? Yes, like I think you are talking about that majority element concept, right? You can do that, but like, yeah, majority element you can do, but yeah, this is the thing, that this is the majority element case. But you can't do these things in O of 1 space, I think. According to me, like I can't think of any O of 1 space algorithm for checking these prefixes and suffixes. But you can do this one in O of 1, but it is just unnecessarily long code. So why do that? Just use the max element function and check that if frequency of k is equal to the max frequency, then already k is majority element, right? So C out 0. And then actually I think in majority element, it should not be equal, right? Like just tell me one thing, that if this is the array 2 2 2 3 3 and 3, so will you say that this 3 is a majority element? No. Yeah, exactly. So that is one difference. So I don't think you can do it in O of 1 space. Yes, like in this question it is right. 3 can be, like if k is equal to 3 and this is the array, then answer is 0 definitely. but 3 is not a majority element here, so you cannot do that. Okay, so anyways, I check this maximum frequency, and if it is equal to frequency of k, then I printed 0 and I returned. Now I check for prefix. Like return means that if answer is 0, then it will return. If it reaches here, then it means that answer is not 0. So I check for answer equal to 1 by checking the prefix first. So prefix, I loop through the array, and one by one I decrease the frequency of this element. Like first I decrease the frequency of first element, then second element. Like first I decrease the frequency, then I check, like, okay, if frequency of k is equal to 0, then break, because definitely it cannot be majority element then, right? Like if the current element, after decreasing the current element, if the frequency of k becomes 0, which means that if k disappeared from the array, then definitely we cannot delete more elements. Like deleting more will not cause any benefit to us. So I just break here. So if frequency of max element is equal to frequency of k, then I print 1, because after deleting a prefix, this condition is satisfied. Okay, and then I return. Otherwise, I check for the suffix. I start from the reverse. N minus 1, I greater than equal to 0, I minus minus. And fr of ai minus minus. And the same thing here. And actually the same thing. Actually, this whole code is exact same. This part and this part is exact same. And yeah. And like, yeah, you return here if the answer is 1. And if you reach here, then basically the answer is 2. Because neither the suffix nor the prefix was able to make the answer as 1. Okay. So this is the code. Now, any doubt in the explanation or the code? As you can see, this max element function actually takes O of n time, where n is the length of the vector. So in this case, the length of fr is just 21. So I can use this max element and it will tell me the max element in O of 20 time. Okay. So the final complexity would be n into 20. Can I explain the for loop? So did you understand the logic? Like for checking the prefix, I am deleting these elements and I'm decreasing the for loop. I'm decreasing the frequency of that element. And after each iteration, I'm checking that is k the most occurring element or not. So do you get that logic? Yes. Okay. So let's say I am checking for prefix, that whether I can delete a prefix or not. Okay. So this is actually just to make sure that fr doesn't get corrupted. Like I am modifying fr in this for loop, and finally again I am restoring it using, I am storing the temp, I am storing fr in temp first, I am modifying fr, and then again I am restoring it using the temp variable so that I can use it here. Okay. Anyways, so here in this for loop, what I am doing is, like, this I goes from 0 to n minus 1. This is my macro actually. This I goes from 0 to n minus 1, and first of, like, basically in the first iteration it would decrease the frequency of the first element, like a of 0, it will decrease the frequency of 2, right? And then it will check, yeah, first of all it will check if frequency of k is equal to 0. If frequency of k becomes 0, that means we have deleted all the k's from the array. So definitely if we delete any more elements from the array, k will not be there, so that cannot be the answer. So we'll just break here, like it cannot be the answer. So I just break here, and if star max element of fr begin fr end, this just returns the maximum frequency. Like in this fr vector or fr array, whatever, um, the maximum value, this returns star max element. Okay, and if it is equal to fr of k, like if the maximum frequency is equal to fr of k, then basically deleting from 0 till I, that prefix of 0 till I, if we delete that, then the answer will be 1. Like then we can have k as the maximum element, maximum frequency occurring element. So we'll just print 1 in that case, because we can delete the prefix from 0 to I, and in that case the max frequency will be equal to frequency of k. And okay, nice, cool. So any other doubt in code or logic? I had a doubt in the use of set. Like we can increment decrement elements in any order in case of set, but when we need to check variable prefixes, we need to increment specific element at a time to get specific prefix to keep track of frequency, which one is for which element. No, to do that you can keep frequency array also. Like you will keep an array and you will keep a set. You will keep two things, and whenever you change the array, you change the set also. So in that way, you will know that like what is the frequency of each element. Actually, in this case, you don't need to know that what is the frequency of the minimum element. Sorry. In this case, um, in this case, that then it is still be efficient. I mean, why won't it be efficient? Like if set and array both would be used, then why wouldn't it be efficient? Like let's say we have a frequency array of 5, 1, 2, 3, 4, 5, and let's say the frequencies are like 5, 7, 8, 0, and 2. So this set or multi-set rather, this multi-set contains 5, 7, or rather it contains a sorted order, right? So it contains 0, 5, 0, 2, 5, 7, and 8. Now, if you want to decrement some value, suppose you want to decrement this 8, then you will just do fr of 3 minus minus. Or actually before that you will do set st dot erase fr of 3. Then you will do fr of 3 minus minus, and then you will do st dot insert fr of 3. So in that way, like you have essentially decremented the frequency of 3 to 7, and you have also decremented this 8 to a 7. Like you have erased this 8 and inserted a 7. So this will take O of log q time, or like log n time, whatever the number of elements in this set, and this will take O of 1 time. This will take O of log n time. So why would it not be efficient? Okay, got it. Nice. So any other doubt? Okay. So should I move on to the next problem? All right. Okay, so this one is constant subsequence. Constant subsequence. Okay. Alice has an array A of length n, and her goal is to rearrange the array in a way that minimizes the maximum subarray sum of the resulting array. Okay, so there's an array, right? Let's say this is the array. Okay. Now Alice wants to rearrange the elements of this array such that the maximum subarray sum is minimized. Okay. So, however, the constraint is that Alice must keep the relative order of all non-negative and negative elements the same as in the original array. That is, let's say we have these elements 2 minus 3, 4, 0, 5, minus 1. So the negative ones are these, so -3 and -1, and the non-negative ones are these, right? So in the rearrangement, in any rearrangement Alice made, she has to ensure that the order among these 2 4 0 5 doesn't change. Like in any array, it has to be like 2 4 0 and 5, and also it has to be -3 and -1. But you can change the order among these, like -3 you can put here, -1 you can put here, like you can do something like this. So this is allowed, but it is not allowed that you change the order among the negative ones. Like let's say you do this: -1 2 4 -3 0 and 5. So in this case the negative numbers order is not preserved, because initially it was -3 -1, and now it is -1 -3. So you cannot rearrange the array like this. So it is not allowed. So basically, out of all the allowed arrangements, we have to determine that what is the maximum subarray sum is minimum. Like basically, let's say for this array, what would be the maximum subarray sum? I think it would be this, right? This is this has the maximum subarray sum, uh, 10 maximum, right? So for this array, the answer is 10. But let's say we have some other arrangement. Let's say we had something like 2 -3 4 -1 0 and 5. So for this array, what is the maximum subarray sum? Let me just calculate. 4 -1 3. Okay, this is, I think, the maximum, which is 8. So we want to minimize. Basically, in this case, in for this rearrangement, we get the maximum subarray sum as 10, and for this rearrangement, we get MSS as 8. So definite 8 would be better in that case. Like basically, we have to check all the subarrays. We have to check all the rearrangements of the array which are allowed, like which preserve the ordering of negative and non-negative elements. And out of all those arrays, we have to report the minimum of the MSS. Do you guys get it? Like, I hope the question is clear, that you have to print the minimum of maximum subversion out of all the arrays. Okay. So in this case, let's see what the answer is. Even I don't know what the answer is. I'll just write on my code and I'll print the answer. Uh, Actually, that will take too much time. Never mind. We'll skip that for now. But I hope you got the problem. Like, basically, the answer would be 8 or less than 8. If there is some other arrangement which doesn't follow the rules, follows the rules, and has a maximum subarray sum of less than 8, then that would be the answer, or else this would be the answer. So anyways, so what I'm saying is, we want to minimize, right? So how do we do that? And yeah, the sum of empty subarray is 0. So basically you can also take an empty subarray, like for this array, -2 -3 -5. So the answer would be 0 for this array, because you don't need to take this -2. Like ideally it would be -2, the maximum subarray sum, but actually you can take the empty subarray, like you don't take any element. So in that case the answer is 0. Okay, so that is allowed, to take the empty subarray. Anyways, so we want to minimize, right? Now actually, I guess all of you must have done this problem of maximum subarray sum, right? So most of you would have studied that, we use Cadence algorithm in this, that we check that taking the previous is optimal or starting a new one is optimal. So actually, what I'm about to tell you is the same algorithm, like, but in different words. Okay. So let's say we wanted to find out the maximum subarray sum of this array. Wait a minute. Just two. Let's just find out for this: 2 -3 4 -1 0 5. 2 -3 4 -1 and 0 5. So guys, actually, what I do is somewhat different. Okay, so what I do is I like to think about sums of subarrays in terms of prefix sums, right? So so first of all, the sum for a subarray L to R, that would just be PR minus P L minus 1, right? Yes. So yeah, this would be the sum from L to R. So what I like to do is basically I loop through the array. I loop from I equal to 0 to n minus 1, and like uh prefix still prefix still I is just pi, right? And we want to choose a j, like if I want to choose an index j such that pi minus pj is maximized, right? I want to find the maximum subarray sum. So I is fixed. So for a certain I want to find a pj such that this value is maximum, right? So what we'll do, we'll just take the minimum. We'll take the minimum pj. So basically, we can just store that what is the minimum prefix sum up till now. We can store the minimum prefix sum that has come up till now, and we'll just use that to maximize this value, right? So that's my idea here. Now I'll just try to dry run on this, and I'll show you what I mean. Just delete this. Uh, if it allows me to delete. Oh, never mind. So 2 minus 3, 4 minus 1, 0, 5. 2 minus 3, 4 minus 1, 0, 5. So in this case, the initially minimum prefix is 0, and the current prefix sum, that is also 0. Now I loop through 2, so the sum becomes 2, right? And the minimum is still 0, so the answer becomes 2. Answer is 2. Okay, answer, this is 2. Then I go to minus 3, so sum becomes minus 1, right? The minimum is still 0, so basically the answer becomes minus 1. Sorry, maximum, we want maximum, so answer is still 2. Okay, and now the minimum changes to minus 1, right? Now we go ahead, so the sum becomes 3. So sum minus minimum, that is 4, so the answer becomes 4, and minimum is still minus 1. Then we go ahead to minus 1, so this sum becomes 2, and 2 minus minus 1 is 3, so answer is still 4. Then we go to 0, nothing changes using 0. Then we go to 5, so sum becomes 7, and sum minus min, which is 7 minus minus 1, answer becomes 8. So actually that's how I find out the maximum Savarius sum. Yes. So yeah, basically you can actually visualize this in form of a graph. Like basically, um, the Savarius sum is pi minus pj, right? For some I greater than j, we want to maximize this value, right? So now let me think. Um, what I thought was we want to find the minimum possible value. So whenever we hear these three words, we want to find something of minimum, something maximum. So what do we think about? Binary search, right? Like if we find monotonicity and like if we want to find the minimum possible value or the maximum possible value, we try to apply binary search here. Okay, so that's what I try to apply. So let's just think about that. How will I apply binary search here? So basically, what my search would be is that I will check for some mid, for some value of mid, I will check that is it possible to make maximum sub-array sum less than or equal to mid. Like, is that possible to make? Like, I'll try to make the maximum sub-array sum less than or equal to mid. Okay. So I'll answer this question, that how to check this thing. But before that, I want to tell you a visualization, a creative visualization. Okay. So think about it. We want to keep the relative order of all non-negative and negative elements the same as in the original array. So what does that mean? Like, let's just take our original example. In that we had 2 minus 3, 4 minus 1, 0, 5. Okay. So let's say this is the original array. 2 minus 3, 4 minus 1, 0 and 5. So what are the positive elements here? The positive elements are 2, 4, 0 and 5. I mean non-negative elements. And the negative elements are minus 3 and minus 1. So basically, whenever you are creating a rearrangement of that array, but you want to preserve this order of the positive and negative. So essentially, what would be doing? Guys, tell me, in the first index, what can come? Yes, we can definitely. We can, like, in this first index, either only 2 or minus 3 can come. Okay. So let's say we put 2 here. Like, basically, let's say we put 2 here. So 2 will get crossed. Then in this index, what can come? Either 4 or minus 3. So let's say we put minus 3 here. So minus 3 will get deleted. Now what can come here? Either minus 1 or 4. So let's say I put minus 1 here. So and now here only 4 can come. Now only 0 and only 5 can come because all the negative elements have vanished. So we have only one option, right? So this is the way of visualizing that if we cannot change the order of these positive and negative elements, this is how we create an array. This is how we can create an array which satisfies these conditions, that we cannot change the order of positive and negative elements. Okay. So this is how I will create an array which will, like, I'll try to create that array which will have MSS less than or equal to mid. Okay. So guys, okay. Now one more thing. So yeah, MSS, as we just saw, that is the current prefix minus minimum prefix, right? That's what I told you right now. So what we can actually do is, as long as this MSS doesn't exceed, like, what are mid, like we are checking for mid, right? We want to ensure that the subarray sum is less than or equal to mid. So as long as it doesn't exceed it, we can keep adding positive elements. Like, guys, what will happen if we add positive elements? It will increase this current prefix, right? So MSS will get increased. So if we can add positive element and this MSS doesn't go greater than mid, then we can keep adding positive elements. But as soon as adding one more positive element will increase MSS greater than mid, like, yeah, as soon as inserting one more positive element, if that creates a condition such that the MSS becomes greater than mid, then we cannot add that positive element. So we would have to add a negative element, right? Because that would decrease the sum, that would decrease the prefix, right? So I just write on this on this example. So let's say we want to make just a minute. So yeah, this was the original array, right? 2 minus 3 4 0 5 minus 1. So I showed you that this one has a sum of 8. So let's check that for 7 do we have a sum. Okay, so the array we have is 2 4 0 5 and minus 3 minus 1. Okay, so positive elements are 2 4 0 5 and negative elements are minus 3 and minus 1. Okay, so currently my array is empty, right? Now we want the now right now let's say our image is 7. Okay, I want to check whether there exists an array which has MSS less than or equal to 7. Okay, so basically we want that our MSS doesn't exceed 7. Okay, so we'll try to do that. So first I'll insert this positive element here. So this becomes 2. So right now our MSS is 2. The maximum Savarez sum is 2. Now if we add 4 here, it is still less than 7. It is 6 right now. Now if we had 0 here, then it is still less than 6, right? Yes, I am explaining that only. Like we are checking for 7. That is there any arrangement for which MSS is less than or equal to 7? So we'll try to make an array such that the maximum sum doesn't go beyond 7. How 7 came? We'll do binary search. Like we'll start with some low and some high, then we'll check the middle element. I'll explain that later. But oh, okay, got it. Okay, cool. So let's say we check for 7. Okay. So right now we want to ensure that MSS is less than equal to 7, right? So we can insert 2 from the positive. Then we can insert 4 from the positive because the sum is still 6. Wait. Yeah, we can insert 4. Then we can insert 0 because sum is still 6. But now we cannot insert 5 because if we insert 5, the maximum subarray sum would become greater than 7. So we cannot insert 5. Okay. So we'll insert the negative element, which is minus 3. So that actually decreases the prefix sum. That decreases the prefix sum, right? So the prefix sum becomes 3. Now if we insert 5, so what would be the maximum prefix? Maximum sum, I mean. So it would be this array. So that would be 8. And we cannot afford that. So therefore, we cannot put 5 here. So we would have to put minus 1 here, the negative element. So we'll delete this minus 1. And here we have to put 5. And you can check that putting 5 doesn't exceed the MSS limit beyond 7. It just like the maximum sum is this, and it is 7. 6 minus 3, which is 3 minus 1 is 2 plus 5 is 7, right? So basically we can just iterate, and as long as the sum does not exceed 7, we can keep adding positive elements. But what is the sum that I'm talking about? Like it is not the prefix sum actually. I'll explain it in more detail. Let's say we have pos is equal to wait, pos is equal to 3, 3 and 5, let's say, and negative elements is minus 4 and 6, and our mid is equal to 7. We are checking if we can make 7 or minus 4 and minus 6. Okay, we are checking if we can make 7 or not. So right now we will create an array. So if we insert this 3, then no problem, we can insert it. Now if we insert this 5, then definitely we cannot insert it because it will go to 8, right? So we'll insert this -4, right? So now actually the minimum prefix becomes -1. Minimum prefix is equal to -1, right? Now if you want to check that can we insert 5 here, so the sum actually, the running sum is actually 4, but the maximum subarray sum is 4 minus minimum prefix, which is -1. So basically you will check, you will store two values, that is what is the running sum, I mean the current prefix sum, and what is the minimum prefix sum. Okay, so minimum prefix sum is -1, so 4 minus -1, that is 5. So 5 is the MSS of this current array. So we can insert this 5. Okay. We insert 3, we insert -4, and we can insert -6 because it is a negative element. A negative element can never increase the MSS. So we'll just insert this -6. So my point was that we have to check for the minimum, like we have to use the formula that uh, MSS is equal to current sum minus minimum prefix, and you need to update this minimum prefix accordingly. Like let's say you insert some negative element due to which the current sum becomes somewhat negative. Suppose it becomes -5, then you have to update this min prefix to -5, and for from the next index onwards you need to check using this -5 value, because that's what I told you, right? In here, that's how we calculate the minimum prefix sum, pi minus pj, where pj is the minimum prefix, right? So actually I'll show you the code first and then I'll take some doubts if you have any. Okay, so I wrote this. Okay, so I took the input. I set the limits, lower and upper limit. I set the limit 1 in 15 because the maximum surveillance sum, that like the maximum of maximum, that could be when all the elements are 1 in 9 and this the n is 2e5. So the maximum sum would be 2e14. So I just kept the upper limit as 1e15. So which is large enough. Okay. Now this B and C are just positive and negative elements. So if AI greater than or equal to 0, then B dot push back AI. Otherwise AI is less than 0, so C dot push back AI. So B is non-negative elements and C is the negative elements. Okay. Now I do while low is less than high, positive elements, negative elements. I create new vectors so that I don't destroy B and C. Now I reverse pos and neg, actually, so that I can just, like, instead of, like, what am I doing? So I am just deleting it from the starting, right? I inserted this 2 and I deleted it from the starting. Then I inserted this 4 and I deleted it. So in vectors, deleting from the end is easier. So I just reversed it so that I have to delete from the end, not the start. So I reversed it. Now I took the mid. Mid is low plus high by 2. And this is the min prefix. This is the sum. Sorry, this is the answer. Answer means the, wait. Actually, I don't think we need the answer. So just ignore that for now. Okay. So min prefix is the prefix, like the min prefix, and p is the prefix, like the current running sum, that is p. Okay. So now I iterate over the, like now I iterate n times. So if pos has some elements, actually if it doesn't have some elements, then I'll just insert negative, right? So this is the else condition for that. Uh, so if pos has some elements, then we do this, and if it doesn't have the elements, then we just p plus equals neg dot back, which means the sum plus equals the element that we are inserting. Then neg dot pop back, because we use that element, and min prefix is min of min prefix comma p. Like we update the min prefix. So if we don't have any positive elements left, then we can just do this. And if we do have positive elements, then we have to check that whether we can insert it or not. So if we can insert it, so basically if p plus pos dot back minus min p, so this is the maximum subarray sum. P plus pos dot back is the sum that would become if we inserted that pos dot back, right? Basically, I'll try run this using this example. Okay, 2405 minus 3 minus 1 made it 7. Okay, so we have this positive array of 2405 and minus, what was it, minus 3 minus 1 and mid is 7. So what I am doing is I am taking, like, I'm basically tracking three variables. Okay, three or two, actually two variables. One is min p and one is p. P is a sum. Okay, min p is currently 0 and p is currently 0. Now I check the first positive element, so it is 2. So if I add 2, like if I add 2 to the array, then this p would become 2 and min p would remain 0. So in that case, the prefix sum would be p minus min p, like it would be 2 minus 0, so which is 2. So before adding, it was 0, right? So I just checked that after adding it would become p plus 2 minus min p, right? The maximum subarray sum, it would become this. So I just checked that is this value less than mid or not. If it is not less than mid, then we cannot add this 2 to the array, right? So I just checked that is p plus ai minus min p or p plus pos dot back minus min p. If it is less than or equal to mid, then I'll just add this min p. I'll just add this, sorry, I'll just add this pos dot back to the array. So I'll do, like, I'll add to this p plus equals pos dot back. And since I use this pos dot back, I'll just delete it from the array, which is pos dot pop back. Okay, and then I update the min p. Actually, I don't need to update the min p because the p is increasing, so definitely min p cannot decrease, but I still did it for some reason. So yeah, if p plus pos dot back minus min p, this is basically maximum subarray sum. If that is less than or equal to mid, then p plus equals pos dot back. Like we are actually adding it to the array, then pos dot pop back, then ignore this line, it is not required, and min p is equal to min of min p comma p. Like this is not required actually because p is increasing. Now otherwise, like this is the case where we can add the positive element. But what if we cannot add the positive element? We would have to add the negative element, right? So if we have negative elements, then we can just add the negative. We just add the negative element. So the sum plus equals neg dot back, neg dot pop back, and answer, ignore this line, and min p. I update the min p because I'm decreasing this p, right? So I have to update this min prefix sum. So I updated this. So basically, yeah, if we are not able to insert this positive element, so we would have to insert this negative element if we have negative elements. But if we don't have negative elements, then we are gone because we cannot add the positive element and we have no negative elements. So that means that we cannot make this maximum subarray sum. Like we cannot make MSS less than or equal to mid. So I just do flag equals false and then break from the loop. Like this flag I set to true here. So if at any point we run out of negative elements and we cannot add some positive elements more, then I just set this flag to false and I break. And in the end, if flag is equal to true, then high is equal to mid. That is basically it is like this, right? 0 0 0 1 1 1. The binary search is like this, and we need to find the first one. So if the current position, suppose the current position is this, we check that it is 1, right? So definitely the answer cannot be more than here, right? It cannot be more than that. So high is equal to mid, and otherwise low is equal to mid plus 1. Like if we find a 0, if the current index is 0, then the answer cannot be from here. So it will be only after the low index, right? So I did low is equal to mid plus 1. And when the while loop exits, that is while low less than high, so when low becomes equal to high, I know that that is the answer. So I'll just print low, right? So this is the logic here. Now, if someone has a doubt in any part, or you want me to repeat any part, so just tell me. Can I explain minus such part? Okay. So basically, do you get that part, that I can answer this question, that can I get a maximum Savarez sum of less than or equal to k? Like if I have some k, then I can answer this question. I can answer this question, that can I get a MSS of less than or equal to k? Like you get that, right? We can answer this question. Okay. So let's say, and we need to minimize k. No, like basically, suppose the answer to the, let's say we have sample test case. Let's say we have this test case -2 3 0 2. Okay. So they have given that the answer is 3, right? So that means the maximums we can get MSS as 3, right? So if I ask this question for k equal to 4, that can we get an MSS less than or equal to 4? Then the answer would be yes or no. Yes. So for 4, the answer would be yes. And for anywhere greater than or equal to 4, like for all greater than or equal to 4, the answer would be yes, right? And for 3 also, answer would be yes. And for less than 3, like can we get a maximum solution less than 3? Like less than, if k is less than 3, like can I get maximum solution less than or equal to 1? Is that possible? What would be the answer for this? It would be no, right? Because the minimum that we can get is 3. So the answers follow a pattern, that initially the answer are 0. Like for 1 the answer is 0, the 2 is the answer is 0. For 3 the answer becomes 1, and for every upper number the answer is 1, where 0 is no and 1 is yes. So we can do binary search on this. We have to find the first one. All right. So any other doubt, anyone? uh Garv, any doubt? No one is saying that they have a doubt, so I'm assuming that they don't. Or if you do, okay, someone does. And lastly, why can't we say here that the case with min MSS would be when pos neg are alternate? Alternate, that doesn't. What if pos is not equal to the number of positive elements? What if it is not equal to negative elements? Then what would you do in that case? Like let's say we have 4, 4, 4, and 4, and we have -2 and -2. So you can't even alternate this. So what would you do? Still, won't it give minimum possible MSS due to max randomness? I'm not sure. I mean, what's your algorithm? That's what I'm asking you. Like, if you have unequal number of positive and negative elements, then how will you alternate between them? You cannot even alternate, right? Because in this case, negative is smaller. So if you try to do that 4 minus 2, 4 minus 2, and 4. But now you have run out of minus 2's. Now what will you put here? Will you put 4, 4 here? So in this case, this Savara sum is very large. I mean, it might be the case that this is the answer, but your algorithm doesn't seem rigorous. Like, what would you do in that case if pos is not equal to negative? Make sense? Okay. So, I think no one has a doubt. So, I'll end this problem. And this was actually the last one that we could do, that I could do. Okay. Yeah. So, bye, guys. Thanks for joining in. I'll see you guys next time.